What's the life expectancy of Betelgeuse?
Well, the star itself,
Yes.
if you consider the main sequence lifetime, probably a few million years.
One violent eruption changed everything we thought we knew about Betelgeuse. During the 2019 to 2020 Great Dimming, the star blasted scorching material into space at nearly 200,000 miles per hour, where it cooled into a dust cloud that hid part of its light. Years later, Hubble and Gemini North pointed to something even stranger, a hidden companion about 1.6 solar masses, separated by just 52 milliarcseconds. Was this unseen neighbor behind the chaos all along? The star that reached a historical minimum. For a week in February 2020, Betelgeuse fell to the faintest brightness ever recorded in the modern era of precise photometry. Between the 7th and 13th of the month, the star sat at 1.614 magnitudes plus or minus 0.008, according to the Nature paper that later reconstructed the event in detail. That number is worth pausing on, because magnitude is one of those astronomical measurements that seems to run backwards. Lower numbers mean brighter stars, so a jump from around 0.5 to 1.6 sounds small, but actually represents a dramatic loss of light. Betelgeuse had shed roughly 2/3 of its normal output. A star that ranks among the 10 brightest in the entire sky had slipped down the visible pecking order until casual observers noticed it with their naked eyes. Amateur astronomers checking Orion in January and February were writing to observatories asking whether the star had already exploded. It hadn't, but something was wrong with the pattern. Betelgeuse is a known variable, and astronomers had been charting its rhythms for more than a century. The primary cycle runs on a beat of roughly 400 days, driven by the star's own radial pulsation as its enormous envelope expands and contracts. On a good cycle, the brightness swings between about 0.0 and 1.3 magnitudes. That range was familiar. February 2020 blew straight through the bottom of it. Reaching 1.614 wasn't a slightly deeper trough, it was the deepest dip in more than a century of monitoring. And the timing didn't align cleanly with any predicted minimum in the 400-day cycle. The star was fading harder, faster, and later than the model allowed. Something was happening on Betelgeuse itself that the pulsation math could not explain. The clue that shifted the whole investigation came from where the darkening lived. When astronomers resolved the star's disk with high-resolution imaging, they discovered the fade was not uniform. The southern hemisphere of Betelgeuse had gone roughly 10 times darker than usual, while the northern half looked closer to normal. That is a jarring piece of data. A star pulsing in and out along its 400-day cycle should dim across its entire visible surface at once, more or less symmetrically. What Betelgeuse showed instead looked like a stain, a localized shadow draped across only one side of the disk. If one hemisphere fell to about 10% of its usual brightness, while the other side stayed lit, what does that tell you about what was really happening on that surface? A simple fade, or something far more localized? 10 times darker on one side is the sentence that ended the just a normal cycle interpretation. Whatever was dimming Betelgeuse was not a rhythm playing out symmetrically inside the star. It was something physical, something spatial, something with a definite location on the surface or in the space just above it. And that reframing is what turned a photometric curiosity into a full astrophysical investigation. That lopsided darkening is the clue that prompts the next question. What actually left the star to create that shadow? In the next chapter, we follow the trail of hot gas that Hubble tracked, speeding outward from Betelgeuse's surface, then cooling into the very dust that hid its light. The numbers are specific, the motion is measurable, and the story is nothing like a quiet fade. So what exactly did Hubble see flying out of Betelgeuse before the dust cloud formed? The outflow. Hubble saw superheated plasma tearing away from Betelgeuse at roughly 200,000 miles per hour. That is the number that anchors the entire outburst story, and it came from ultraviolet spectra taken in the months leading up to the February minimum. While ground-based telescopes were still watching the star dim, Hubble was already measuring the material that would cause the darkness, and it was moving fast. 200,000 miles per hour is difficult to picture, so it helps to translate. That is about 55 miles per second, or fast enough to cross the diameter of Earth in roughly 2.5 minutes. A jet of hot gas, rising off the star at that speed, reaches the outer atmosphere of Betelgeuse in weeks, not centuries. That timescale is critical because it means the star could physically produce a light-blocking cloud on human observation timescales, not on geological ones. The way Hubble tracked it was through ultraviolet spectroscopy. When hot plasma moves toward us, its emission lines shift slightly toward shorter wavelengths, the same Doppler effect that raises the pitch of an approaching siren. Between September and November of 2019, Hubble recorded exactly those shifts in ultraviolet features tied to material rising off the southern hemisphere of the star. Dense, heated gas was streaming outward. The direction of that outflow matched the same face of Betelgeuse that would later go 10 times darker than usual, and the timing lined up perfectly with the collapse in brightness that followed. That sequence is the physical chain the observation confirmed. Hot material ejected from the surface, plasma expanding and cooling as it rose, then condensing into a cloud of silicate dust, roughly the size of a small planet drifting across our line of sight. Ultraviolet caught the eruption. Infrared, months later, would catch the dust. Together, they closed the loop on what had blocked the light. If gas was moving that fast, what does that imply about how quickly the dust could form and how suddenly a star of that size could actually dim? The Harvard and Smithsonian Center for Astrophysics release put the answer plainly. The plasma cooled as it expanded, and once the temperature dropped low enough, silicate grains began to condense out of the flow. That process can happen in a matter of weeks at the distances involved, which is why a star that had looked steady for a century could lose 2/3 of its light in a single winter. The outburst wasn't just violent, it was efficient, and that reframes what the February 2020 minimum actually was. It wasn't a mystery brightness dip searching for a cause. It was the light curve of a specific, measurable event, a mass ejection from a specific hemisphere, moving at a specific speed, cooling into a specific cloud at a specific moment in the star's history. Every piece of that description came from data, not inference. That fast-moving outburst explains the 2019 and 2020 event, but it also raises a bigger question. Was Betelgeuse's surface already changing long before this episode? In the next chapter, we step back and look at a 15-year reconstruction of the star's photosphere, a timeline showing this wasn't a one-off glitch, but part of a longer surface evolution. So what does a decade and a half of data reveal about how Betelgeuse's outer layers were behaving in the years before the Great Dimming? A star that was already rewriting itself. A decade and a half of data reveals that Betelgeuse's photosphere had already been rearranging itself long before the Great Dimming ever began. That is the central finding of a 2024 paper published in Astronomy and Astrophysics, which reconstructed the star's visible surface across roughly 15 years of high-resolution observations. The technique the authors used is called tomography, and it works on a star in much the same way a medical scan works on a body. A single image of Betelgeuse is just a two-dimensional snapshot, but if you combine hundreds of spectra taken at slightly different wavelengths, each one sampling material at a slightly different depth or velocity in the atmosphere, you can rebuild a layered picture of what the outer envelope is actually doing. Applied across 15 years of archival data, that method turned a scatter of individual observations into a running film of the surface. The film is not calm. The reconstructed photosphere shows enormous convective structures rising and sinking, hot regions brightening and fading, cooler patches drifting across the disk, and the overall pattern shifting on timescales of months to years. Betelgeuse was never a smooth, glowing ball. It was a churning surface that reorganized itself repeatedly across the observation window, with individual features large enough to swallow the orbits of the inner planets. What that longer view reframes is the Great Dimming itself. Looking at February 2020 in isolation, it is tempting to describe the event as a sudden accident, one violent moment where a well-behaved star broke its own pattern. The 15-year tomography does not support that framing. It shows a photosphere that had been actively reorganizing for years, with convective activity intensifying and the surface pattern shifting in ways that laid the groundwork for a large ejection. When the outburst finally came, it didn't erupt out of a quiet star. It erupted out of a surface that had already been building toward instability. If Betelgeuse's outer layers were shifting like that for 15 years, does the 2019 outburst look more like an isolated accident or like one dramatic moment inside a longer breakdown? The tomography favors the second reading, and that reframes the through line of the whole investigation. The February minimum, the 200,000 mile/hour outflow, the dust cloud, and the 10 times darker southern hemisphere all belong to the same story as the slower photospheric shifts recorded in the years before. They are the acute symptom of a longer condition. The Great Dimming was the loudest event, but it wasn't the beginning of the change. It was the moment the change became impossible to ignore. That perspective also matters for what came next in the investigation. If Betelgeuse's surface had been evolving on decade-long timescales, then any hidden influence tugging on that surface, any second body sharing the system, would leave its own fingerprints across the same 15 years of data. A 15-year surface history sets the stage, but the next piece of evidence changes the entire system, not just the surface. In 2025, a team using Gemini North and speckle imaging resolved something that had been hidden for decades: a second star orbiting the giant. Its mass, its brightness, and its position are all measurable. So what does a 1.6 solar mass companion just 52 milliarcseconds away actually do to the story of Betelgeuse's long cycles and eventual fate? The hidden companion, a 1.6 solar mass companion sitting 52 milliarcseconds from Betelgeuse, turns the entire system into a binary and rewrites the meaning of nearly every long cycle astronomers have measured on that star. That detection came in 2025 from a Gemini North speckle imaging campaign that finally resolved something earlier telescopes had never been able to pull out of the glare. The instrument responsible is the Alopeka Speckle Imager, mounted on the 8.1-meter Gemini North telescope on Mauna Kea. Speckle imaging solves a very specific problem. Earth's atmosphere blurs starlight on timescales of milliseconds, so any long exposure smears fine detail into a shimmering blob. Alopeka gets around that by taking thousands of extremely short exposures, each one effectively freezing the atmospheric turbulence in place, then combining them mathematically to recover the sharpness a telescope in space would deliver. Right next to a brilliant star like Betelgeuse, that trick is exactly what you need to isolate a faint object hiding in the halo. The numbers the team pulled from those frames are specific. The companion sits at an angular separation of about 52 milliarcseconds, which is roughly 1/20,000th of a degree, a distance so small that only diffraction-limited imaging could resolve it at all. Its mass is estimated at approximately 1.6 solar masses, and its brightness in visible light is about 6 magnitudes fainter than Betelgeuse itself. 6 magnitudes is a factor of roughly 250 in brightness, which is why decades of ordinary imaging never showed it. The companion was always there. It was simply drowned in the primary's light. The discovery team describes the detection as probable rather than absolutely locked, and follow-up observations are already scheduled to confirm it further. But the geometric consistency is striking. The companion's position and estimated orbital motion match Betelgeuse's roughly 2,170-day-long secondary period so cleanly that the 6-year cycle astronomers had been trying to explain with pulsation models for decades now has a much simpler cause. It was another star pulling on the giant from very close range. The proposed name for that companion, honored through an Arabic naming tradition that echoes Betelgeuse's own etymology, is Siwaha, meaning her bracelet. It is a fitting label for a small, bright object circling the wrist of the giant on Orion's shoulder. If a 1.6 solar mass star is orbiting that close, what does its presence do to the gas and dust around Betelgeuse and to the long cycles astronomers have been measuring for over a century? The dynamical answer is that a companion at that separation is essentially plowing through the outer envelope of the red supergiant on every orbit. It stirs the atmosphere, drives shocks through the outflowing material, and can accelerate the rate at which Betelgeuse loses mass into space. The 2,170-day cycle stops looking like an internal breathing pattern and starts looking like the signature of a second body sculpting the envelope from the inside. A hidden companion changes the architecture of the whole system, but it also forces the hardest question. What does this mean for Betelgeuse's final chapter? The next chapter brings JWST's infrared view into the picture and ties the outburst, the dust, and the companion into a single storyline about how this star is actually evolving toward its end. So what does James Webb see now that earlier telescopes couldn't? And how does that reshape the timeline of Betelgeuse's final moments? Rewriting the timeline. James Webb sees what optical telescopes cannot: the dust itself. Its infrared instruments, AMIRI and NIR-CAM, the mid-infrared instrument and the near-infrared camera, are designed to look at exactly the wavelengths that dust glows in, rather than the wavelengths dust blocks. When Webb turns that capability on Betelgeuse and the space immediately around it, the picture reveals what the earlier outburst story could only hint at. The mass loss is not symmetric. That word matters. A lone red supergiant, pulsing evenly along its 400-day cycle, should shed material in a roughly spherical pattern. Betelgeuse doesn't. The dust structures around it are lopsided, with denser plumes drifting in some directions and thinner outflows in others. That geometry is exactly what you would expect from a star whose outer envelope is being stirred by a close companion. Every 6-year orbit, Siwaha plows through the outer layers, driving shocks and channeling the outflow into asymmetric shapes. The infrared view and the July 2025 companion detection are telling the same story through completely different instruments. Webb also proved that stars like Betelgeuse do explode, and it did so with a specific case. In June 2025, a supernova catalogued as SN2025PHT appeared in the galaxy NGC 1637, roughly 40 million light-years from Earth. Webb had already imaged that patch of sky before the explosion. When astronomers pulled the archives, they found the doomed star sitting exactly where the supernova later appeared. The progenitor was a dusty, carbon-rich red supergiant that had been nearly invisible in optical Hubble images, roughly 100 times fainter than what Webb could pick out in infrared. It was the first published JWST detection of a core collapse supernova progenitor, and it confirmed the sequence in the most direct way possible. Dusty red supergiant, heavy mass loss, then explosion. Betelgeuse fits into that exact category. It is dust-wrapped, actively shedding, and sitting in the late stretch of its evolutionary life. But the timeline is where the story lands, honestly. Current evolutionary models place Betelgeuse in core helium burning. not the far more advanced carbon-burning stage that would signal an imminent explosion. The consensus estimate for remaining lifetime sits somewhere between 10,000 and 100,000 years. That is a long window on human timescales, and nothing in Webb's imaging changes it. The 2019 surface mass ejection was violent, but it was a symptom of an active outer envelope, not a countdown to core collapse. No acceleration has been detected in the primary 400-day pulsation, which would be the clearest early sign that the internal clock had shifted into a shorter, burning phase. If JWST can already see the asymmetric mass loss and the dust geometry, what would a real acceleration in the star's internal clock actually look like? And would we recognize it before the neutrino burst arrives? The honest answer is that we probably would if it happens slowly enough. A steady shortening of the pulsation cycle over months or years would be measurable with existing monitoring networks. But the final collapse itself gives almost no visual warning. When the iron core finally implodes, a burst of neutrinos escapes the star hours before the shockwave reaches the surface and the light show begins. Those neutrinos would be Earth's real alarm. Detectors like Super Kamiokande and IceCube stand ready to catch that pulse, and a few hours is enough time to point every instrument on the planet toward Orion. Every major observatory, from radio arrays to gamma-ray satellites, would swing toward that single point in Orion within minutes of the alert reaching Earth. The next galactic supernova will be the most thoroughly documented event in the history of astronomy, and Betelgeuse remains the leading candidate for earning that distinction. James Webb captured something genuinely strange around Betelgeuse, a lopsided dust geometry that fits a hidden partner, a companion of about 1.6 solar masses sitting just 52 milliarcseconds away, and proof that dusty red supergiants really do explode. The final moments run 10,000 to 100,000 years long. Does that make the explosion feel closer or farther for you?